In this video, we're going to look at two population means with unknown standard deviations. So what does this mean? Well, suppose you want to compare two hourly wages of, say, men versus women in the same field with the same experience. And you want to compare the percent of people under 25 who use a cell phone versus people who are over 25. So now we're going to compare two means or two proportions. You're going to work with two groups, and the groups are either considered independent or dependent. When we say independent, we say the groups consist of two samples that are selected that they're no way related to the other group that we are looking at, this other sample group that we're looking at. The parameters tested are using independent groups, and they could be population means or population proportions. Dependent, we're going to call those matched pairs, and this consists of two samples that are dependent. They're somehow matched before and after, so like you give them a treatment, you check to see what they were before the treatment, and you check to see what they are after the treatment. Now, since we are doing hypothesis testing, we are going to use the same 7 steps. We're going to write a claim. We're going to write the opposite. We're going to assign what the null or HO is, null hypothesis or HO. You're going to determine if it's right, left, or two-tailed, and the critical region. Now remember, we talked about the critical region. That's the region in which we decide to accept or reject the null hypothesis. We're going to find the test statistic. We're going to find that p-value, and we're going to look at the test statistic. We're going to compare it against the critical value, and we're also going to do the p-value and test it against the alpha, or alpha divided by 2 region. We're going to reject or fail to reject the null hypothesis, and then we're going to write some sort of statement. Now, the only thing that's different for 2 samples versus 1 sample in Chapter 9 is Step 5. Step 5, the test statistic will change. So it is said the sampling method is said to be independent when the individuals selected for one or more sample do not dictate which individuals are to be in the second sample. Dependent against when we talked about the matched pairs, when the individuals selected in one sample are used to determine the individuals in the second sample, or that the individuals in the first sample has some sort of effect on the second set of individuals for the second sample. Dependent samples are usually called matched pairs, this is what we talked about before just a few moments ago, and it's possible for an individual to be a matched pair against themselves. That's like when we give a patient treatment, so the before and after, to see whether or not the treatment was successful. So now we're going to determine whether the given samples here are, the sampling method is independent or dependent. A researcher wants to know whether the price of a single night stay in a Holiday Inn Express is less than the price in a one-night stay at a Red Roof Inn. The researchers randomly select towns in which the location of the hotels are close to each other and determines the price of one-night stay. Now these are dependent. Why? Because they're close together. And if you have the Red Roof Inn is much, much less expensive than the Holiday Inn, then people are going to go to the Red Roof Inn. So these are dependent. One will affect the other. The prices and one will affect the other. And that's because they're close together. Now, if they were in towns in which they're on opposite sides of the town, they would probably not be a matched pair or dependent. A researcher wants to know whether the state quarters, introduced in 1999, have a mean weight that is different from the traditional quarters. The researcher randomly selects 18 state quarters and 16 traditional quarters and compares the weights. Now these are independent. The weight of the state quarters are not going to affect the weight of the traditional quarters, and there's no real relationship of before and after or matched pair kind of situation with this. So unlike the previous example, these are independent. So in this particular section, we're going to be doing a t-test. So we're not going to do proportions yet, we're going to do a t-test, which means that we're going to be focusing on population means of two populations using independent samples. We're going to do dependent or matched pairs in a later section in Chapter 10, but not in this one. So the two samples are independent if they come from two distinct populations. There are a couple of things that are required for the hypothesis test regarding two populations' means, which is mu1 and mu2. With unknown deviations, the requirement is a t-test for two simple random samples. First of all, the populations from the samples are drawn are normally distributed, or the samples for each sample group has to be larger than or equal to 30. And the samples must be using simple random, that should be random, not rand, sampling, and the samples are independent, and for each sample, the sample size is no more than 5% of the population size. Now the test statistic changes. So the test statistic is the x sub 1 minus the x sub 2. Now, x bar sub 1 and x bar sub 2, these are the means that we get from our samples. And then we have the means that we get from the populations those samples come from, which is mu1, mu2. And notice here the doing, instead of s squared divided by n, it's now s sub 1 squared over n1 plus s sub 2 squared over n2, and then you take the square root of it. So the test statistic changes because we now have two means, two potentially population means, and then of course our standard deviations for each sample will be different. And also the number of items we get from each sample could be different as well. The degrees of freedom, of course, will change, and so you'll see that that is a big gnarly equation, and we're going to put that into our spreadsheets, and we'll talk about how to get those in our spreadsheets in just a moment. Conservatively, you can take the smaller of the two, which is n1 minus n2, or n2 minus, or n sub 1 minus 1 and n sub 2 minus 1. Now, here's the thing. Typically, most of the time, they use this really big, complicated degrees of freedom. So unless it says to use the conservative degrees of freedom, we're going to be using this large and complicated. So we're going to talk about how to put that into our spreadsheet at the end of this video. When we talk about doing a hypothesis testing of two populations, usually the claim is that the means are equal, or one group has a higher or lower mean than the other. So we will assume not our ha, but our ho, our null hypothesis, ho, that our claims will have comparison means, and ha will be either they're not equal to, one is larger, or the other one, or the one that we thought was initially larger, or the second group is larger. So our ho, by default, will always be the means are equal, and then our ha would be not equal to, the first group is larger, or the second group is larger. A study is done to determine if Company A retains its workers longer than Company B. Company A has a sample of 15 workers. Their average time with the company is 5 years with a standard deviation of 1.2. Company B samples 20 workers, and their average time is 4.5 years with a standard deviation of 0.8. Assume the populations are normally distributed. Now this is really important because remember my sample sizes are smaller than 30. Remember we have to have at least 30. And so we're going to do the appropriate hypothesis test, and is this a means or proportions? Well, we know that this is a means because it talks about the means. Are these independent? The answer is yes, because they're not working, one person is not working at both companies. Now one person may have worked at one company and then the other, but doesn't say that, so we assume that they are independent. What is our random variable? Well, our random variable will be x bar. State the null and alternative hypothesis. So my ho by default is that mu1 is equal to mu2. And my ha is, I believe, what do I believe? A study has determined that Company A retains its workers longer than Company B. So I'm going to assign mu1 would be for Company A, and mu2 would be Company B. And that's just because it's what I see first. And so I believe that my Company A retains them longer than Company B. Now we can tell this is, based on the fact this is pointing to the left, this is a left-tailed test. So we know that it is a, right-tailed test. Helps if I know my left from my right. It is pointing to the right. The pointy part is pointing to the right, so it is a right-tailed test. Which distribution am I going to use? And it's a student t distribution because it does not have the population standard deviation, which of course we said mostly that is magical, so we don't typically do that. So, and this is a student t. Now, here's the thing. Before we used to, with a single mean, we do the random variable x is approximately distributed. So we do something like this. We do x is approximately t, and then we put our degrees of freedom here. Now we can still do the same thing here, but the degrees of freedom are going to be much more complicated. And then we would go and find our p-value and all of that. So let's talk about the calculator that I'm going to need. So now we're in chapter 10, and I like to label everything. Now, the t-score is much, much, much more involved. So you'll see that I have a parenthesis, and every time I have everything lowercased here when I'm doing a call in Excel, that means I'm grabbing the cells that have those bits of information in them. If it's uppercased, then that means that it's a call with an Excel. Now you'll notice here is how I found my degrees of freedom. This is very, very long and involved. And I would try to, if I was you, take a moment to build this calculator, use these numbers that I have, and see whether or not your numbers are matching up to my numbers. Now remember, I'm going to put in the 0.05. That's the alpha that will be given to me. If I need it to be a two-tailed test, I go ahead and calculate that now. I have my first x bar, so I'll enter that. I have my first standard deviation, I will enter that. Now this does not necessarily reflect the problem that was up above, just so you know. We're going to go back and I'm going to give you the answers to that in a moment. My N1, this is for the first population, and my mu1. Now we assume, unless told otherwise, that we're going to put in mu1 and mu2 to be 0. So mu1 and mu2 will be 0. Typically this will be the same as mu1, so it could be something else. The homework may give you something else. If it does give you something else, please use that, but typically, since it doesn't really matter with the test statistic, the t-score, that you might as well put in the same number, and I used 0. You're going to put in your second x bar, your second standard deviation, your second sample size, whatever that happens to be. Now the degrees of freedom are super long. So the first thing is, you're in this cell, you're going to put in equals. You're going to put a parentheses, and you are going to grab your first standard deviation cell. You're going to square that cell. You're going to divide by the sample size of that first grouping, so that would be that. And then plus, now we're going to grab the second standard deviation for the second sample, which is here. Be sure to square that. And then divide by, and then you're going to do the n, your second size, and then you're going to square that entire numerator. So this entire piece from this parenthesis to this parenthesis, and then the square 2 is the numerator, which is the formula that's up above. And then it's going to be divided by. Now notice I have two parentheses, one parenthesis here, and this one closes the entire denominator. So in this cell, these are all the things that I am typing in by grabbing the appropriate cells. So I'm going to take the standard deviation of the first grouping squared, divided by the N1, the quantity squared. So I'm going to have my first standard deviation squared, divided by the sample size, and that whole thing gets squared. And then it's going to be divided by my sample size minus 1, my first sample size minus 1. And then I'm going to repeat that again for the second standard deviation. So the second standard deviation squared divided by the second sample size, the quantity squared, and then that piece here gets divided by the second sample size minus 1. This parenthesis closes this parenthesis. These are all the calculations that I have to type in here. Now remember, anything that is lowercase means that I am grabbing the cells with that bit of information, which is why I label the crap out of everything here. And then my t-score for alpha divided by 2, I will use this if I have a two-tail. If it's a left or right tail, I will use this. If it's left tail, it'll be negative. If it's right tail, I will take the positive of this. This will be my critical value. My t-score then gets calculated, my x bar 1 minus my x bar 2. So those are these numbers up here. This 4.5, I'm grabbing this cell that has 4.5, and I'm grabbing this cell that has a 6.33. Minus, and then of course, mu1 minus mu2 should be 0 most of the time. Not always, but most of the time. Parenthesis here, and I have a parenthesis that closes it, the numerator, and then I do the square root of the standard deviation of the first one squared divided by its sample size plus the standard deviation of the second one divided by its sample size, closing these parentheses off. Again, Anytime I have capital letters, that means I am grabbing the Excel call or the function. Anything that is lowercase means I am actually grabbing the cell that has that. So when this says alpha divided by 2, I am grabbing the cell that has alpha divided by 2. And then I'm grabbing the cell that has the degrees of freedom. Same thing here is I do the t-distribution right, t-distribution two-tail. Make sure you put in the absolute value so you're choosing the most right value, because the t-distribution two-tail requires you to grab the most right value. Now, as I've said before, every time we are doing a t-score, we are default going to the left. So if you are a right tail test, your t-score, remember that it is the absolute value of this. And you're asking me, why is that happening? Well, if you remember when we did the confidence interval, this is chapter 8. So here was our mu, and we did the confidence interval, and we said we're 95% confident that it's in this region. And that's how we did the confidence interval, is that we ended up with a left and a right tail. Now, these values were my t alpha divided by 2, and this was also my t alpha divided by 2. This was a negative value, and then we said, oh, just make this the positive value. So every time we're doing the calculations, by default, we are using the negative is being calculated. So if you need a right tail test, you might want to make a little note here to say, hey, if I need right tail, it should be the positive of this. Okay, so basically this is just repeated. I don't know why I have it twice, so you can actually just ignore this part because I really have it twice. And then of course, here is my decision. I grab my alpha from up above. So this, where it says equals alpha, I am grabbing the cell up above that has the alpha. And here I'm entering the appropriate p-value. Now the p-value for this particular one should have been the same, but let's assume that we were doing a right tail test on whatever is here. So what I would have grabbed for the right tail test wouldn't have been that number. I would have grabbed this number right here. And that would have been my right tail test, which is 0.90772. And you can tell you that that is a very large p-value in reference to what I'm usually using when I talk about p-values and alpha. Okay, so coming back to here, now that we know how to build this spreadsheet, let's assume that the numbers that we had in there were the appropriate values, which they weren't for this example. Now, when I took a screenshot of my chapter 10 calculator, I took it when I actually had something else entered in there. So what was my p-value? So I went out and I went to my spreadsheet and I put in my appropriate values and what was my p-value. Well, before we talk about the p-value, let's talk about what the critical value was. Remember, that comes from my t alpha. So my critical value here was the t alpha. And when I did my t alpha, I ended up with a negative. Now remember, I'm right-tailed, so I take the positive. So I'm going to do 1.761. So that was my t, that's my critical value. Now my t-score that's calculated, so the t-score that gets calculated, which is that big and exciting formula, so my t-score, which is calculated, this ended up being a 1.61106. Now I just gave you more than you need. Let's talk about what's going on here before we do the p-value. So if I look at my t-distribution, of course, here's where my mu is. My critical value is here. This is where my critical value is. That's my t alpha. And this is where my t-score landed. It actually landed to the left side. So that tells me, without actually looking at the p-value or confirming what's going to happen with the p-value, is that I'm going to fail to reject because I'm in the fail to reject region. So what is my p-value for that particular t-score? Well, my p-value for a right tail test is 0.064. So that's the p-value associated to this t-score. Now, this is the alpha 0.5. We can see that this number is larger. So the decision is fail to reject. And that's because of two reasons. Is my t alpha, which is my critical value, is greater than my t-score, and I'm right tail. And then confirming that is my p-value, which is equal to 0.064, is greater than my alpha, which is 0.05, and that's my alpha. So both of them confirm that I am going to fail to reject that there is a difference between the company A and B in terms of how long people stay there. So what is my conclusion? Well, I would write something along the lines like, there is not sufficient evidence to support the claim that company A retains workers longer than company B. They're about the same. So that's what my conclusion is. And again, do make sure that you have something similar to this in your spreadsheets. All of these things are grabbing the cells in my spreadsheets that are labeled these things. And of course, if it does have capitals, that means the capitals here means that I'm using the built-in Excel functions. So that's the difference. Do make sure that you actually put that information in here. Do the equals, the absolute value, parenthesis, T invert of alpha divided by 2, and then grabbing the cell that has your degrees of freedom. This also is grabbing the cell of alpha divided by 2, so it's grabbing this cell. Although you could probably just do it on the fly. But anyways, that's it for this video. Nice short one, and we will see you in class.